After completing this lesson, you will be able to explain why full fine-tuning is impractical for most people, understand how low-rank adaptation works and why it's efficient, calculate memory requirements for different approaches, explain quantized low-rank adaptation and when to use 4-bit quantization. Choose between low-rank adaptation and quantized low-rank adaptation for your projects. Full fine-tuning means updating all the parameters, weights, in the model during training. For a 7B, 7 billion parameter model, parameters $7,000 memory in FP16, 114 GB just for the model. Training memory, 42, 56 GB, with gradients, optimizer states, activations. Hardware needed. High-end GPU, like A100, 80 GB. As you can see in the Llama 3 paper, Llama 3 was trained on 16K H100 GPUs and an H100 GPU. It costs around $30,000, if you can even get it because it's not in stock. For Llama 3.1 70B, memory needed, SU80 400 GB. Hardware cost, multiple $30,000 H100 GPUs. Who has that? Large companies only. The reality, too expensive for individuals, requires specialized hardware, long training times, high electricity costs. We need a better way. Enter low-rank adaptation and quantized low-rank adaptation. Instead of updating all parameters, low-rank adaptation adds small adapter matrices that we train instead. Instead of fine-tuning the actual weights of the models, we are fine-tuning low-rank matrices instead. Low-rank adaptation adapters, what we actually train. During training, keep W frozen, don't update. Only train A and B, effective update, DW, TARS, B, X, A. At inference, merge W new, W plus, B, X, A, or keep separate and add on the fly. For example, when we multiply these low-rank matrices, we can get a matrix of the same shape as the actual weights of the model, but instead of having to fine-tune 25 weights, we only have to fine-tune 10 weights. Llama 3 8B, full fine-tuning, trainable parameters, 8,000. Memory, a 48 GB Llama 3 8B with low-rank adaptation, R16. Trainable parameters, say 16,000, 0.102%. Memory, 14, 20 GB, 95% memory reduction. How many dimensions in the adapters? Common values, 8, 16, 32, 64. Higher, SIRS, more capacity, but more memory. Scaling factor for low-rank adaptation updates, often set equal to R, alpha by R, controls how much low-rank adaptation influences the base model. Which layers to add low-rank adaptation adapters to? Common choices. Python, attention only, most common. Target modules, soon, qproj, kproj, vproj, autoproj. Attention plus FFN, more capacity. Target modules, chersh, qproj, kproj, vproj, autoproj, gatiproj, upperproj, downproj. Dropout for regularization, often 0 or 0.05. Higher dropout, less overfitting but slower convergence. Quantized low-rank adaptation plus 4-bit quantization of the base model. Q low-rank adaptation is actually when we also quantize the base model and, for example, represent the weights with 4 bits instead of 16 bits. In computers, everything is represented in bits, zeros and ones. Representing numbers, 4-bit quantization, use only 4 bits instead of 16 to represent each weight. Result, 4x, smaller model, 7B model, 14 GBs, 3.5 GB, minimal quality loss, surprisingly, adapters still trained in higher precision. Method, model size, training memory, GPU needed, suffice the full fine-tuning. 7B at FP16, 48 GB, 880 GB. Low rank adaptation. 7B, FP16, 20 GB, RTX, 4090, 24 GB. Quantized low rank adaptation. 7B out of 4-bit, 8 GB, RTX, 4070, 12 GB. For your Tesla P40, 24 GB. Model. Method. Fits. Quaduance 7B, full FT, no, 48 GB. 7B, low rank adaptation, yes, 20 gigabits. 7B, quantized low rank adaptation, yes, white tag GB. 13B, full FT, no, 78 GBs. 13B, low rank adaptation, no, at 35 GB first. 13B, quantized low rank adaptation, yes, on 15 GB. Then 30B, and quantized low rank adaptation, and yes, and 22 GBs. 70B, the quantized low rank adaptation, no, and 48 GBs. With quantized low rank adaptation, you can train 13B models on your 24 GB GPU. Research findings. 4-bit quantization causes minimal quality loss. With good training data, quantized low rank adaptation matches low rank adaptation quality. Sometimes even better, quantization acts as regularization. When quantized low rank adaptation quality might drop, very small datasets, 100 examples, tasks requiring high numerical precision, already small models, 1B parameters. Recommendation, try quantized low rank adaptation first. Only use low rank adaptation if you notice quality issues. Rule of thumb, training memory, shows model memory x2, 3. Results, 7B, low rank adaptation, 20 GB fits. 7B quantized, low rank adaptation, 8 GB fits easily. 13B, low rank adaptation, 35 GB too big. 13B quantized, low rank adaptation, your 15 GB fits. If you run out of memory, 1. Use quantized low rank adaptation instead of low rank adaptation, 4x reduction. 2. Reduce batch size, per device trained batch size, 1, 3. Use gradient accumulation with steps, 1, 4. 4. Reduce sequence length, max secu length tone 24, 5. Lower low rank adaptation rank, R-WOD 8 instead of R16, 6. Enable gradient checkpointing, trade speed for memory. You have enough VRAM, model fits comfortably, you want slightly faster training. You're training a very small model, 1B. Task requires high numerical precision. You want to avoid any potential quality loss. Limited VRAM, want to fit larger models. Training 7B plus models on consumer GPUs. You have good quality training data, 100 plus examples. Memory is your bottleneck. You want to experiment with higher ranks or more target modules. 7B models, either works, but low rank adaptation is fine. 13B models, use quantized. Low rank adaptation, only option that fits. Your first project, start with quantized low rank adaptation to have more headroom. One, what is the main idea behind low rank adaptation? Answer, Instead of training all model parameters, low-rank adaptation trains small adapter matrices, A and B, that are added to the frozen original weights. This reduces trainable parameters from billions to millions, 99% plus reduction. 2. Calculate. If a 7B model has 7 billion parameters, approximately how many parameters are trainable with low-rank adaptation, our 16? Answer: approximately 816 million parameters, which is about 0.2% of the total. The exact number depends on target modules, but typically around 10-20 million trainable params. 3. What is the difference between low-rank adaptation and quantized low-rank adaptation? Answer: low-rank adaptation, base model in 16-bit, adapters trained. Quantized, low-rank adaptation, base model quantized to 4-bit, adapters still trained in higher precision. Quantized low-rank adaptation uses 4x less memory with minimal quality loss. 4. Your Tesla P40 has 24 GB VRAM. Can you train a 13B model with regular low-rank adaptation? Answer: no. A 13B model with low-rank adaptation needs 35 GB VRAM. However, you can train it with quantized low-rank adaptation, 15 GB. 5. What happens if you increase the low-rank adaptation rank from R16 to R64? Answer: more trainable parameters, 4x more. More model capacity, can learn more complex patterns. More memory usage, higher risk of overfitting on small datasets, slower training. Using your project from previous lessons. 1. Which model size do you want to use? 1B, Tiny Llama. 7B, Llama 3 8B. 13B, Llama 3 13B. Larger. 2. Calculate memory needed. Method 1, low-rank adaptation. GB, Method 2, quantized low-rank adaptation. Geared GB 3. Will it fit on your Tesla P40, 24 GB? 4. Which method will you use and why? Example. One, full fine-tuning is impractical. Needs expensive hardware most don't have. 2. Low-rank adaptation trains adapters instead of full model, 99% plus parameter reduction. Quantized low-rank adaptation, Boischer's low-rank adaptation. 4-bit quantization, 4x smaller base model 4. Memory savings are huge. Full FT, GI 48 GB, 7B model. Low-rank adaptation, 20 GB. Quantized low-rank adaptation, job at 8 GB, 5. Quality is preserved, especially with good training data 6. For Tesla P40, 24 GB. 7B, both low-rank adaptation and quantized low-rank adaptation work. 13B, only quantized low-rank adaptation fits. 30B, quantized low-rank adaptation barely fits 7. Low-rank adaptation hyperparameters. Rank 16 is balanced. Alpha. Scaling, usually bichar. Target modules. Which layers to adapt? Now that you understand how to make fine-tuning affordable, let's learn about choosing the right model. Lesson 1.5, Model Types and Selection. Want to learn more? Low-rank adaptation paper. Low-rank adaptation. Low-rank adaptation of large language models. Quantized low-rank adaptation paper. Quantized low-rank adaptation. Efficient fine-tuning of quantized LLMs. Unsloth. Documentation. https://github.com/unslothi. Unsloth.